Another one of the gas laws that we have to work with is called Charles' law. And in the last lesson, we looked at Boyle's law, where we didn't see any changes in temperature. I didn't even talk about temperature. But with Boyle's law, temperature is not changing, and all we're doing is changing the volume and the pressure. With Charles' law, we're going to change the temperature, but we're going to assume that the pressure doesn't change. And that would be true if we have a situation where the volume is allowed to change so that the pressure equalizes. And if you allow the volume to change, it will equalize. So let's say that we have something like a balloon, where the balloon can stretch. The pressure outside and the pressure inside will equalize. That's just a law of nature. And so if you allow that to happen, either with stretching a balloon or with maybe a piston that's allowed to move up and down, if you heat the gas or cool the gas, which changes the pressure, then the volume is going to automatically change so that the pressure inside and the pressure outside is the same. The only time that won't happen is if you have a setup where the volume can't change. So like if I put the cover on here, the volume can't really change because this is a fairly rigid container. But if it was something more elasticy like a balloon and it could change, then the pressure would stay the same. So that's the kind of scenario that we're looking at when we talk about Charles' law. And so this, again, I think is fairly intuitive to you, that if you heat up a gas, it's going to expand. And if you have this gas in a container where it's allowed to expand, then it will, such that the pressure inside and the pressure outside is the same. So let's look at this mathematically. And the way that I like to do it is just to write TV first, because then I can remember what I'm working with for variables. So notice that there's no P in here, and we're assuming then that the pressure is held constant. Now, when we use Boyle's law, we had 1, 1, 2, 2. But with Charles' law, these are not inversely proportional. These variables are directly proportional. And what that means is if one gets bigger, the other gets bigger. If we raise the temperature, the volume's going to go up. So in that case, we have to say 1, 2, 2, 1, like that. So once we have our formula, then we can start plugging things in and looking at how this is going to work. So another thing that you need to know about this formula, though, is that we have to use kelvins. Now remember when we were talking about Boyle's law, I said it doesn't matter what units you use for pressure and volume, as long as they're the same on both sides of the equation. And that's going to be true here for units of volume. It doesn't matter what you use as long as it's the same on both sides. But for temperature, you have to use Kelvin, because we have to be using a system where 0 means 0. And in the Kelvin scale, 0, well, I was going to say degrees, but Kelvins don't use degrees. 0 kelvins means absolutely no heat, just like 0 volume would mean absolutely no volume. So it's important that we use a system that works that way. Otherwise, we don't get good answers at all. All right, so let's say that we have a scenario where we have gas at, let's say 200 milliliters of gas at, and I'm going to say 298 Kelvin. Because that's room temperature. Actually, you know what? I'm not going to say 298 Kelvin because I didn't bring my calculator and I won't be able to do the math. Let's call it 300 Kelvin, which is very close to room temperature. And then maybe I'll be able to do the math in my head. All right, now let's say that we're going to heat this up and we're going to double the temperature, which is a lot of heat here, but that's all right. So after we make this change, we'll say that the temperature is going to equal 600 Kelvin. And we want to know then, what will the volume be? Now maybe you can guess this because you can say, well, if I double the temperature and it's going to increase, then I might be doubling my volume. And you can see from the equation that that is exactly the way it works out. But let's plug numbers in just so that we can say we did it. So the first temperature was 300 Kelvin. The second volume, so pay attention to that, the second volume is what our unknown is. We don't know that. The second temperature is 600 Kelvin. And the first volume was 200 milliliters. All right, so to solve for V, we're going to take our 300, divide both sides. So 600 divided by 300 would be 2. 2 times 200 is 400, so there we have it. Indeed, the volume does double. And that's really the extent of Charles' law. It's a fairly straightforward operation where when you increase the temperature, you're going to increase your volume. If you decrease the temperature, you're going to decrease the volume. And the only tricky part here is to make sure that you use kelvins, because if you don't, you're going to get the wrong answer every time. So just as a reminder, if you were to get a problem that gives you Celsius, you have to add 273. So let's just remind ourselves of that. Kelvin is equal to Celsius plus 273. And make sure you use kelvins.